Oh, please.
Okay, so everyone, we'll go ahead and get started. So welcome. This is actually our very first CS research seminar this fall. In fact, it's the first time we've done it since I joined the department 3 years ago. I'm really excited to introduce everyone to Professor EJ Jung. So Professor Jung has a PhD in computer science from UT Austin. Professor Jung joined the Department of Computer Science in 2010 and most recently was department chair until this past July. Her research interests include distributed systems and network security, as well as solving problems in blockchain. And today she's going to be discussing her research on proof of stake in blockchain. So with that, I'll hand it over to Professor Jung.
All right, thanks. So I actually prepared this to be very basic to my research questions that I am asking in my research project, not knowing what you already know. So please, please, please ask me tons of questions. I love to be interactive, and you can pretty much interrupt me at any moment. So if you ask questions in the chat, John will be monitoring it and letting me know. And feel free to just, be loud and say, hey, why does that work that way? And I'll be more than happy to answer. So without further ado, we're going to start by asking the question of what exactly is blockchain, and we'll talk about what people actually do with it, and what do I do about it, and what can you do about it. So that's going to be the plan for today. So let's start with what is blockchain. Blockchain literally is a chain of blocks. And what is a block? A block is a data storage unit. So I want you to think about like a book that you have, or at some point in your life, maybe you had written an essay for your school, and it's basically a bunch of pages. And each page has a limit in how much data you can put in. Imagine when you're given that, let's say you can only bring one page to your exam, and this is going to be your cheat sheet. You've got to have seen people doing this whole printing and then shrinking through the copier and all that business, right? Even with that shrinking, still there's the limit on how much data you can pack into a single page. So blog is the same thing. It has the storage limit, and you can pack it in as much as you want by compressing your data and all different things, but it still has a limit in terms of how much data that you can put in. And once you have that, obviously you gotta have more than one page in your essay so that you can contain all the thoughts that you have. So blockchain chains blocks in kind of data chain fashion so that you can keep growing the size of the data that you keep. So how do we link these pages? So if you are writing an essay, or if you're doing anything that is not electronic, you can either staple the pages, you can put them in the binder, or you could actually submit the things with the page numbers. So if I get the stack of the paper from you, I can check the page numbers and say, oh, okay, this is how the pages are ordered. Blockchain does something slightly different. So I'm going to actually go to the next page to explain how it links the pages. I'm going to give you a quiz. And I'm asking you to absolutely randomly guess how we do it. This is 9 a.m. in Pacific time. You're absolutely guessing. Let's see these two color blocks on the left. I have some red and some blue, okay? Imagine these are basically a big pot of paint. How much from the red paint box and how much from the blue paint box do you need to combine and mix it together to get this kinda pinkish, kinda purplish, I don't even know the name of this color, kind of color? How would you make that guess? If I just give you the right side, this pinkish purplish block, and say, here are red paint and blue paint, tell me the recipe. How do I get to this pink purplish thing? Most of you will go like, I don't even know the name of the color. There's no way that I can just come up with a recipe. of course, you can try every possible combination, right? So you can try 1 part red, 9 part blue, 2 part red, 8 part blue. Like you can do all those things. And if you find the right recipe, you can actually put it next to the box that I gave you and say, oh, okay, they're the same color. I found the winning recipe. But when things are a little off, you gotta try again. It's not like you are given this paint that you can somehow magically whip it and separate it into red and blue so that you can just tell me the recipe. Separation of color, if you think about it, is a very expensive process. You could actually do it if you really, really, really want to by spending lots of money. There are all these like chemical processing machines that you could employ. But if you think about it, just buying a bunch of paint and trying out different recipes is way cheaper. And sometimes it could be actually even faster. So this is a classic example of what we call trapdoor function in computer science. Trapdoor as in that you can go in very easily, but this is a trapdoor, meaning that it's very difficult to go out. Make sense? And that's what it means to be one way. That going one way is very easy, but going the other way is very expensive, slow, sometimes very painful. So this is an example of what we call trapdoor function, meaning that what we can do is to use this to link the pages. So I'm going to go to the next one a little bit. If you think about the mathematical functions f, what does that actually translate into? Given y value, it's very difficult to find the value x that gives you the exact y. So if I give you the x, meaning the recipe of how to mix these colors, it is easy to verify that I gave you the correct x by just running it through the function. But it is very difficult for you to go from y to the inverse of y. And how do we use it in blockchain? We use it in kind of like that shrinking page from the cheat sheet. So imagine that you get one page. Okay, I'm going to do this smaller shrinking copier thing, magic, to get a tiny bit like your thumbnail kind of thing, very tiny image from it. And I'm going to put this as part of the second page. Okay, and I'm going to do the same thing, including that thumbnail. I'm going to take the entire page 2 and run it through the copier again and get again very small thumbnail that I'm going to put in block 3. And I'm going to keep doing that. And what does that give you? Even if I lie about the page number based on the small thumbnail image, that you can tell, oh wait, that page number is wrong. So in reality, what we actually do is we put block 1 through the hash function f, and this is the output of running block 1 through the hash function. In reality, it is not 42. It is way longer random looking numbers. And we put that number into the second block. Okay. And including that number, the entire block 2 goes through F, and 61 is going to be the output of the block 2 through the one-way hash function. So, okay, I can see that. I can see that this is kind of linking the previous page to the next page. What's so exciting about it? Let's say I want to cheat. Let's say this is actually the essay that I submitted. And after I submitted, after the deadline, I realized that I should have mentioned this particular reference that the fact that professor told me to use, and that was in syllabus. I was supposed to do it and I forgot about it. And I already submitted it. The deadline is over. Maybe I can actually change my block 2 to something else. And I'm going to say, oh, I did use that reference in this new block 2 prime. For me to be able to do that, I need to satisfy two things. First, I need to include 42 from the first page in my block 2 prime. And whatever this block 2 prime, when I run it through the f function, let's say this one gives me 43 this time. I need to somehow make this match, right? Because block 3 is supposed to have the output from block 2. So if I get the new page with the reference that I wanted to include, then this output is supposed to be here. That's how the blockchains are all chained. So wait, 43 is not okay because this is not going to match what the third page already is. So what do I need to do? I have to change block 3 too. Once I change block 3, it's going to give me a different number from 33. I have to make a new block 4. Okay, if I have to rewrite the whole entire essay, it's unlikely that the teacher doesn't notice that what you submitted is different from what you claim to have submitted at this point. So this is the keyword that has been super important in the blockchain world, immutable. Immutable means that it's not changeable. And it's not like impossible, but it's very difficult. Because once you see this number, it is difficult for you to figure out the block 2 prime that matches 61 and still have all the right content that you want to include. Any questions so far? All right. And I really mean it. Please interrupt me as much as you want. So what do we do with this? Because the blocks are chained through this one-way hash function, it's really difficult to rewrite the past. Once you have submitted something in a blockchain, then somehow coming up with a different page that matches all the hash values is very difficult. So what do we do this? What do we do with this? Let's say we want to have some sort of a shared database, and especially for the shared database for banking system. I'm pretty sure that every one of you have some experience with electronic banking by now. So when you log into your bank website, you get to see the balance, you get to see the statement, you get to see the history of transactions. All those things are stored in a database. And every transaction that you make, let's say you pay the rent, you pay your cell phone bill, all this movement of money is called transaction. And for us to support the transaction properly, we need 4 different things that database do. The first thing is what we call atomicity, all or nothing. So let's say I'm paying John, let's say I owe him for some sort of like a dinner that we had together before pandemic started, long time ago. It feels like years ago now, sadly. Let's say I needed to send him some money. It is not okay for the money to disappear from my account and not appear from his account, right? So that's what it means to have all or nothing. Debit and credit have to both happen, all of them, or none of them happen. And you may be surprised at how this is a difficult thing to do over the scale of the internet. Many of you are using messengers, and if you think about it, what appears on your chat screen should appear at your friend's screen as well. The message is sent on your side and not received on your friend's side. That is actually very common, and we try to solve it by duplicating the send underneath so that the message definitely appears on your friend's chat screen. This atomicity over the scale of the internet is actually pretty difficult. Consistency means that everyone sees the same data, meaning that if I see that my balance is, say, to give you just a random example, let's say my balance is $3,000. Then not just that I see $3,000, but everyone else in the bank should also see $3,000. So if I try to pay rent, I guess I cannot pay San Francisco rent out of $3,000. So let's say I try to pay a cell phone bill. Then the bank should also see that I have enough money to pay for my cell phone bill and go from there. And if the bank says that, oh, EJ only has $30, I'm not going to be able to pay my cell phone bill, right? So that's the consistency. Isolation is everything runs as if I am the isolation, like I am the single user that's using this bank currently, which is sad if it's true for the bank, right? You want the bank to be very successful and be able to run a bunch of transactions at the same time. When I'm paying my cell phone bill, John should be able to pay his cell phone bill as well. So the isolation makes sure that things can run in parallel and still not break the state of the data. So here's an example. Do you guys even know what ATM is? I hope so. Okay, all right. So when I was your age, I tried to get money out of an ATM and ATM machine crashed on me. So it deducted money from my account and somehow did not give me the cash. And it was like $70 that I was trying to get out of an ATM, which is at that point, at least in my life, it was a lot of money. So I was not leaving that machine until someone comes and gives me the cash. Why did that happen? Because back then, the banking database was not that stable. So when things were happening at the same time in the network, sometimes the machine cannot handle all the transactions and kind of go belly up. Durability is something similar. Let's say I put money into my account, then that should stay there. It should not disappear out of thin air. So taking the acronym, we call this asset property. And this is what every transaction supporting database should have. And surprise, surprise, you can actually do this in a blockchain. You may have heard of cryptocurrency like Bitcoin. And how does that work? Because if you think about it, bank gets a lot of money from us just to keep track of all this data. And providing you this web internet banking service, they actually charge you unless you have so much money in your account. So it's kind of surprising that bank argues that they spend so much money taking care of this database, and blockchain seems to be able to replace that. So how does that work? The database in a bank works on balance. So let's say this is the bank's database, and here A has $100 and B has $200. Instead of storing balances, let's say we store the history of transactions. So transactions will look like A started his account with a balance of, say, 200, and B started his balance with 100, and A pays B $100. If I run through these transactions, then I will arrive in the same conclusion as the bank's database that keeps track of the balance. So if we keep track of all the transactions that happened, we should be able to match what bank keeps in their databases. okay, I guess that's fine. But then I really don't like the idea of everybody gets to see where I'm spending money and who I'm paying, which, by the way, surprises me how Venmo transactions are so public. It really blows my mind. Like, okay, I'm a security person, so I'm way more paranoid than an average person. I give you that, but still, like, I go to Venmo and I can see, like, oh yeah, that friend must have had ramen with that friend last night, because that's exactly what Venmo transaction says. Like, oh, the friend B is paying friend A with a cute little emoticon of ramen will get $30. And it's like, okay, so and so had ramen dinner yesterday. Like, why would you make that public? It just blows my mind. But like, again, I'm a security person. I'm way more paranoid than others. So if someone can explain this to me, please do. So I don't know about everybody uses Venmo in public way, but I don't care to share all my transactions in public. So what this cryptocurrency thing does, kind of smart way, is instead of saying real names, we're gonna use what we call pseudonym. Pseudo just means fake. You can kind of think of it as a nickname. And instead of making a nickname readable, so it's easy for you to remember, they're actually going to make it very, very difficult to remember by giving 128 or 256, depends on the blockchain system you use, a random string of numbers and letters. So what it happens is that instead of actually seeing the transaction history with the real names, you're going to see the entire transaction history, but with the fake names and nicknames. So if I present a proof that, oh, I am the owner of the nickname B, for example, again, in real blockchain, nicknames are very, very long random looking string. So it's almost impossible for you to memorize it. If I can somehow prove that I am that particular nickname B, then I can issue a new transaction and spend away the money that is in that particular account. Okay. So once you have this history of all the fake names and somehow you can verify that who has this particular fake name, what can we do? You can spend the money, you can send the money, you can receive money. Actually, receiving money, you don't even need to prove. You can just give the pseudonym and the pseudonym gets paid. And because of the way blockchain works with the one-way hash function, we just talked about the immutability of the blockchain. Immutability makes the whole history of transactions consistent and durable, meaning that once it's written into a blockchain, it's very difficult for it to change the content. So it's going to make it very easy for someone to say, oh, I can check how much balance that you have. And that's how the cryptocurrency started. And this is actually pretty much how Bitcoin works and how Ethereum works as far as the currency goes. Well, that sounds all good. So what's so fun about it? I'm gonna skip ahead a little bit. Unfortunately, things don't go as well as we hoped for. So the first problem that I worked on blockchain is to find out what applications that run on blockchain, particularly Ethereum blockchain, are Ponzi schemes. So if you're not familiar with the Ponzi schemes, this is also called pyramid scheme, that how if you're a very, very early investor into this scheme, you make some money, but later a lot more people end up just paying for it, but never receive the return. So this kind of works in like a number one person gets paid from number two and number three, and number two person gets paid from 4 and 5, and 3 gets paid from 6 and 7, so that you can see that as you go to the next level, more people have to put in money to support the earlier investors. So it usually ends with about thousands of people putting in money and never getting a return at the end of the day. So I did the fraud detection in Ethereum. That was my first research in blockchain. And we actually are still continuing because the Ponzi schemes are evolving. So the detection scheme has to evolve as well. So this is an ongoing project if you're interested. And more importantly, also I should have actually mentioned this earlier, Professor Hayden Lee will give you a talk later in this semester, and he's helping me with this work as well. Blockchain can fork. And what does the fork mean? Let's say we are at block 12. We all agree on the history of transactions up to block 12, but there are two different candidates for block 13. Let's say different people made two different block 13s. That's what we call fork. And how many different blocks can come in a single level? I have seen up to 10. And in average, you get a fork in every 6 blocks. So if you look at the blockchain in any part for 6 of them, you will see at least one of them had a fork. And why is fork bad? Because fork creates a double spending problem. So let's say A had $100 in block 12, okay? And in block 13, A pays B $100. And in block 13 in blue, let's say A pays C $100. We can't let A spend that much money, right? We cannot pay both of them. We can only pay one of them. So we have to decide which one of them is what we call canonical. Meaning that which one of these blue and red blocks is going to be the authoritative database that says, okay, A paid B, end of the story, A is now 0, B is 100 plus. And this happens a lot. And this happens incidentally because of the internet being the scale of the internet, but it also happens because people want to game the system. So for example, let's say A paid B, okay? And it later found that, oh, if I pay C 100, I can get way more goods in return. Let's say B offers one iPhone for $100. It's an example. iPhone is never $100, but let's say A is getting 1 out of B and A is getting 2 out of C. Then A wants to cancel the transaction. But in blockchain, you cannot rewrite the past. So what does A do? Oh, I'm going to create a parallel world where I actually get 2 for the same amount of money. So what A can try to do, A can try to game the system by saying, oh, you know what? This is the correct block 13. You guys all should use block 13 that is in blue. Red one was a fake. So my work is about consensus, which means that how all the blockchain users agree on one block such that we don't have the double spending problem, and also we don't have any this gaming system kind of people taking advantage of others. So if you think about it, if B really truly believed that A paid him and B goes and spends it, and then it gets canceled, B is gonna get in trouble, right? The same thing happens in Venmo. Like if you get paid and actually spend away the money right away, Venmo balance is not finalized for 2 days. So you may be actually spending way more money than what you actually meant to do. And if you actually do like search for like Venmo heist, you'll see like it's way better now, but there are many, many incidents. So how do we actually do this consensus? We do 2 different things. One is to say, hey, how about we do really, really difficult work and see if we can somehow prove that, oh, I'm really spending a lot of work for this system, so I deserve to pick what is the right data for this blockchain. That is what proof of work is, and you may have heard of the miners that spend a lot of electricity and hash rate. All of that comes from what we call proof of work. It's similar to trying every combination of the paints in the paint example that I gave you earlier. So it kind of is wasteful. It spends a lot of electricity. So just Bitcoin alone, miners use about, actually more electricity a year than an entire country of Switzerland uses a year. So it's a lot of electricity. And you may be noticing that the climate is kind of crazy right now. It's called climate crisis, not climate change. It is definitely contributing to that fact. So we as in the whole blockchain industry, we're actually trying to switch to something that is more energy efficient. And that is proof of stake. And that's what I usually use in my consensus algorithm because I'm very aware that climate crisis is real. So here's what you can kind of think of. Usually the proof of stake runs as if it's a voting system. And one coin, quote unquote, it doesn't have to be a coin, but I'm providing as an example of a unit, equals to one vote. And imagine that everybody votes. And let's say if there's a fork, a lot of people can go ahead and vote and say, oh, I think red should be the canonical one or the blue should be the canonical one. And let's say majority voting wins. That's one way to do the consensus because all this voting is also a transaction that goes on the blockchain. So everybody can see everyone's voting records and do the tally and see which one is the winning block, which is kind of okay, right? That kind of works, right? You guys are old enough to have seen some elections in your life, okay? And there may have been in your life that one election that you kind of felt like, wait, that person won that election, but no one in my circle likes that guy. Wait a second. It turns out that voting rate was only 40%. So imagine that you have 10 people in the system to vote, right? Only 4 people out of 10 voted. Let's say out of these 4 people, let's say 3 people voted for red and 1 person voted for blue. Okay, so based on these 4 people that actually voted, red is gonna win, right? But if you think about it, there are 6 people who were silent who didn't vote. And out of these 6 people, just to give you an extreme example, 6 of them could have been thinking, oh yeah, blue should be the canonical. So what happens is that when the voting rate is so low, the result of voting doesn't actually reflect the reality. And this is going to be a problem in blockchain because voting costs. For you to be able to vote, you need to have these coins, right? So you need to have asset, you need to be rich to be able to vote. So that's one thing already. It's like, that doesn't sound exactly fair, right? I mean, in democracy, no one is paying to vote. So it's like, wait, that sounds a bit weird. The second thing is, even after you have a coin, for you to vote officially, you have to write that into blockchain. And for you to write into blockchain also costs money. You have to make this transaction electronically, send it to the correct people, and you have to keep sending it until it gets to these people. And you have to make sure that these people will record your votes properly by paying them small transaction fee. So voting costs. So you know what? I think someone else is gonna vote. I know everybody else is going to vote, it's okay for me to be lazy. I'm gonna sleep in. I'm not gonna vote. I'm sure that enough people vote and things will not change even if I vote. Unfortunately, this kind of called for what we call tragedy of commons. That when everybody thinks that, oh, I can be a little selfish, I can be a little lazy. The entire commons is actually the pasture where sheep could come and eat the grass. So when enough people think that way, the voting system fails, which is unfortunate, but it's the reality. I think you're old enough to have seen some example of tragedy of commons in your life. So what we do is called incentive compatible consensus algorithm. And I'm going to explain in the particular context of blockchain what it means to be incentive compatible. So this is an attack that I discovered with a colleague, and I call it gateway attack because it kind of keeps the gateway. Well, I just told you about how you have to pay some people to get your vote recorded in the blockchain. And these people are called block producers. They produce blocks, meaning that they collect the votes and other transactions and publish the blocks so people can maintain the blockchain and use the blockchain. And they get paid for doing the job. I mean, they should be paid because it's a lot of work to do. So what they do is that they sit around the table and they take turns to make some money. So to make things simple, let's say for every block they create, they get $10. I made $10, I made $10, I made $10, and the next one is thinking, it's my turn, I'm gonna make $10. And let's say there's a new person coming and say, oh, I want to join the table and I want to be able to produce blocks and get some money too. This person will definitely say no, thinking, wait a second, it's my turn to make money. You're not coming, like you're not cutting the line here. I'm not gonna let you in. The next person goes, it's my turn. You're not cutting in front of me. The next person will say, So as they take turns, no one is going to let a new person in. So what it means is that even if there are more users and more voters in the system, you will not be able to get more block producers. And you basically get this collusion, a kind of a monopoly of a cartel of the current block producers that just get more and more money as the users join the system and pay the fees. So this is what I call gateway attack, preventing new block producers from joining. And as you think about it, this is like, yeah, of course, like that's no brainer. That's what happens in reality, right? Unfortunately, this really happens in blockchain. So if you heard of Cosmos actually had this happen early days. So they had to do some special arrangements for the newcomers to join this kind of join transaction. Came with a special tag that they had to be processed. So that's one way they dealt with it. So what does it mean to be incentive compatible? Incentive compatible means that the action that I take, let's say there are two different actions. One that is good for the system, like letting the new block producer in, and the bad one that is bad for the system, like saying no to the new block producer every single time. The good one is going to get rewarded to the point that, let's say I was going to make $10 out of making a block, and this new person comes and says, hey, I'll pay you $10 right now. You don't have to do any work if you let me come in front of you. And when it comes to your turn, you will make money again. So here's reward for you to do a good thing for the system. Such that this net gain from this action it's going to be positive. Okay. And if it's bad, then we're going to give a penalty such that net gain is going to be negative. And designing the whole protocol this way, make sure that the users of the system will behave in the way that benefits the system. And proving that comes from game theory, where Professor Hayden Lee comes in. And I can probably tell you more about it if you're interested. And for me to really see that this is happening, I have an Ethereum analysis project that looks into the miners' behavior and show that, yes, miners really act selfishly. And this is what happened that hurt the system. There are a bunch of examples that happened already. And again, if you're interested, I can tell you more about it later. But right now is going into the end of our time. And I think I'm gonna pause here and open the floor for questions. So just to end with the promised questions, like what can you do about it? You are more than welcome to join my research project. And right now, the things that are open, we do have the analytics kind of full right now. I have 2 students working on it, but if you're interested in the incentive side of it or the fraud detection side of it that I mentioned earlier, the Ponzi scheme, we have room for some people. All right, with that, I'll conclude the talk for today. Any questions?
Yep, I have a question regarding the pseudonyms. If they, like, are they the same for each person or for each user? If it's, for example, user B and pseudonym for him will be something like B and a lot of numbers and letters, will it be the same over the system or it will be changed for some transactions?
So the nicknames have to remain the same. So I can verify the transaction history of that particular nickname to be assured that that particular nickname has enough balance to spend. So for example, let's say you are B and you are trying to pay me, then I would not accept your payment unless I see that you have enough balance, right? So if you change your name in the middle of the process, then I will not be able to verify the balance through the transactions. So you can change your nickname. Let's say you got a nickname C, then you will need to add a transaction that shows the money was transferred from B to C so that I can check the balance of C. So yes, you can change your nickname, but if you change your nickname, then the money has to follow.
Okay, thank you.
If people are feeling shy, they're welcome to also answer or ask questions in the chat, and I can ask them verbally if that is helpful, if it's late or early for folks. Actually, I have a question, if I may.
Sure.
I'm just curious, what are some of the more interesting applications of blockchain that are maybe a little bit unexpected that you've heard of?
I think I'm not surprised by the existence, but I'm surprised by the scale is DeFi. DeFi stands for decentralized finance. And decentralized finance means that it is not going to be a company or person that runs this financial project, but it's going to be an application. And it's interesting because application is uploaded to blockchain already. So you cannot actually change the behavior later without making a big announcement and change on the blockchain with the next version and all that. So you get transparency on how this financial apps work. And right now, the amount of money that is locked in DeFi is about $4 billion. So I knew that was going to be a good application of blockchain. But I have to say, I'm a little surprised at how eager people adopted this system. So I think that's partly because Wall Street didn't do so well very recently, except for the tech market, the stock market. So that may be it, because they saw way better earning from blockchain related projects. But also, I think a lot of people are drawn to transparency, especially from countries where the economic market, like the market is not very stable. Like, certain countries recently had hyperinflation, the value of their currency just plummeted, and people were kind of looking at blockchain as a way to invest in that is more stable than their own currency, and or something that they can invest in without having their government notice. So I think that's coming in bigger scale than I expected.
Follow up on that. I'm curious about like what application do you think that blockchain doesn't make sense? Because like when you say, you cannot rewrite the past, I can think about of a lot of things that like we need to update. Like people make mistake all the time. Absolutely. And like when you say we cannot rewrite the past, it seems to be like pretty limited to me. So I'm just curious, if you have thoughts about that.
Yes. So you should definitely come and talk to me if you're interested in like the details, because one of the things I did a lot when blockchain started to become very hot is to kind of give an investment advice to friends. They'll bring blockchain projects to me and say, hey, is this going to make sense? Is this going to work? And I have to say, 9 out of 10, I'll say no. It's better now, but in the beginning, everyone was just going crazy. Like everything coin was going to make money. So here's an example that doesn't make sense to me. Any data that has to stay private going on the blockchain without having proper encryption is an oxymoron. Because the way blockchain works is that everybody has the same data, and this data is going to give you a power to verify if someone is lying or someone can actually do something, right? Just like the cryptocurrency, if I see that you don't have a balance, I'm not going to accept your payment. So anything that says that, oh, we're going to create this blockchain-based marketplace for this private data that everybody, no one, not even to their family, wants to share, but they're going to voluntarily put it on blockchain just because we're going to give them coins. No, you should not have that. So the private data that should not be public, I'm very like, of course you can do something like secure multi-party computation, you can do homomorphic encryption. There are ways to do it. It's just that not knowing what to do in terms of security and privacy, those are very dangerous. Things that have to change over time, that you need to forget the history. If you need to forget the history, that doesn't work well with blockchain either, because blockchain by definition, you cannot forget. So one of the things that is very difficult to do is to honor the right to be deleted, right to remove your data that is spelled out in GDPR by EU. And California is actually going to have a very similar law in effect in, I'd say, 3 to 5 years. So GDPR says that you have a right to be forgotten. And at any point, if you write to the company and say, delete all my data that you have, the company has to honor it. And if it's written in blockchain, then company can't. It's just written, it's out there. It's not just the company's database, but it's everyone's database that has this data. So that doesn't chime in very well. So one way that blockchain companies are going around is that they only put the encrypted data on the blockchain and delete the key. So even though the data is out there and we're not going to delete it, but it's inaccessible to the point that it's very, very similar to not being able to read it. So all these like privacy issues make blockchain data marketplace expensive because the way that we have to put in the encryption and decryption and key management is quite complex. But this is coming. This is definitely coming, I would say, in the next year.
I have a question.
Sure.
So what's the current stage of the blockchain, and how soon do you think the blockchain will get fully adopted by all industries?
I don't think blockchain will be adopted by all industries, and I don't think it has to. That's what I believe. I may be wrong, but that's what I believe, because blockchain is not good for the real-time responsiveness. So if you want something that happens in real time, blockchain doesn't work very well. When are we going to see the mass adoption? I think we're actually seeing the trajectory in DeFi way earlier than I expected. And supply chain management is happening. It's slowly happening because of the legal reasons, but it is definitely happening. So the things that work well with blockchain, I think the scale, the mass adoption in scale will be happening in the next like 3 to 5 years. Like the food tracing in supply chain, trailer tracing in shipments, those are all happening as we speak. So I think for the ones that is a good fit, I think it'll happen actually fairly soon.
Great, thank you. And I have another question about, you mentioned there are some roles in your lab right now. For the fraud detection or some other roles, what are the techniques you need to be able to do this job, like languages or skills?
That's a great question. So for the fraud detection, you will be using, actually you can use Java too, but most of the packages that we're using for the data mining and machine learning are in Python. So it'll be better for you to know Python. And I think one of the things that I kind of need you to be able to do is to be able to read and understand articles independently. Of course, I'll help you understand, but you need to be able to read like articles that I give you and come back with some level of understanding. So I think that's actually like the most important thing for me.
Got it, thank you.
Sure. Should I answer questions in the chat? I know that we're getting over time.
Yeah, sorry, I was actually trying to, and I realized I was muted. So I can ask the questions, and if you want to be the responder. So from Jose, with proof of stake algorithms requiring communication with multiple stakeholders, this requires a lot of devices communicating with each other. What are some of the challenges this brings to our current network infrastructure, and what benefits will 5G networks bring? Is the expectation that 5G will allow for a quicker adoption of proof of stake or incentive compatible consensus?
I love this question, and I really love this question. And I think the answer is actually no, because right now, how much communication so what 5G really helps is the bandwidth and the speed. So how much information can be circulated at a faster pace. And unfortunately, this can actually create more forks. So consensus can take longer with having bigger number of competing blocks. So right now, my guess is that 5G doesn't necessarily make the consensus faster, but 5G can make the circulation faster. So once the consensus is reached, I think circulating the consensus, proof of the consensus is actually going to be faster. So will 5G make us run incentive compatible consensus better? The answer is also, again, unfortunately no, because incentive compatibility depends on monitors and kind of observers making sure that people are doing the right thing. And observers don't necessarily benefit from the fast circulation, but observers benefit more from, let's say, better crypto at this point, actually. So I think it's going to help in the sense that it will be easier for us to announce once the consensus is reached, but getting to the consensus itself, is actually going to be a little complicated. So one way to think about it is with the adoption of 5G, now cell phones can be a consensus participant. So we'll have more participants, and more participants usually means lower consensus.
Great. So I think we have time for one more question. I think this is actually a really good ending question from Milton. What resources would you suggest to develop working understanding or knowledge of blockchain tech / crypto? And how can students apply for open positions in your lab?
So for the first question, if you are a text person, Binance has a great blog, academy kind of thing that you can read through to get the basics. And once you get the basics, the next step that I highly recommend is, surprise, surprise, Twitter. Twitter has all sorts of the blockchain enthusiasts and researchers posting and sharing their cutting edge stuff. So once you follow Vitalik Buterin and see who responds to Vitalik with the sensible arguments and follow those people, you will get to have pretty good cutting edge knowledge. And of course, if you have any questions, feel free to reach out. How do you apply? Email me and we'll set up some Zoom meeting and we'll talk.
Awesome. Well, Professor Jung, thank you so much for presenting to our students today. I do want to remind our students that every Tuesday for the semester, we'll be actually offering this research seminar. And next Tuesday will be with Professor Jeff Johnson, who will be discussing his research and new book on the psychological basis of UX guidelines. So if everyone wouldn't mind helping me thank Professor Jung virtually, thank you so much.
Thank you.
Thank you.
Thank you.
Hope everyone has a wonderful day.
Have a good one.
Bye.
Thank you.
Thanks.
Thank you.
Thank you.